Okay, we're going to go ahead and start chapter 2 now. So the chapter 2 is entitled Derivatives, and our first section is Derivatives and Rates of Change. This is a pretty long section, so get ready. All right, so we're going to start out with a note about a very special limit. We're going to be studying a limit that will eventually lead us to one of the major reasons why we take Calculus 1. The limit that we'll be studying is called the derivative. It's going to be able to help us find tangent lines to curves, the velocity of a moving object, the instantaneous rate of change of a function. And by the end of the section, we'll be solving some pretty difficult problems. All right, so let's start off here. Most students are familiar with the idea of a tangent line. They've seen it with a circle. So the concept here is that we need to try and find a line that intersects this circle in exactly one point. So what I'm going to do to start with is start with this point here. I'm just going to show a line that intersects not only this point, but some other point on the circle. So right now, this line is connecting 2 points on the circle. We call that line a secant line. It intersects the circle at 2 points. What we want is to try and get a line that intersects at 1 point. So what I'll do is I'll drag this, and that second point is going to start getting closer and closer to my first point. And eventually, when I get there, boom, I get what's called the tangent line. And you can kind of see that this line hits the circle just right there at that single point. And in a geometry class, they tell you that if you draw a line from the center of the circle out to that point, that this line would be perpendicular. That's not going to be important here for what we're doing. What we want to be focusing on is the idea that you start out with a secant line, you start out with a base point here, and you try and drag the second point over to the first point to get that tangent line. So let's go ahead now and look at this idea on a function instead. So instead of having a circle, let me just draw this function. It's probably a third-degree polynomial function. What I want to do is try and find the tangent line at this black dot. So I'll first start out by showing a line that intersects the graph in 2 points here. So this right now is a secant line because it connects 2 points on the graph. I'll take my slider here and I'll drag that second point, and what I'm doing is I'm changing the x value in the function, and it's pulling this point along the function, and I'm going to get it closer and closer to that black point. And about right here, I'm going to zoom in so we can really see what's happening here. And you can see that as I try and get closer and closer, eventually I get right on top of that other point, and I will get the tangent line. So that's where we're headed here. That's the concept. Now, to do this, we have to come up with some sort of plan of attack. So here's what we've got. And the two examples above, what we did is we started with some point on the curve, the black point here. Then we selected some other point different from the first one, the blue point here. Then we drew a line between the two, right? And then we slowly moved the second point so that it became the first point. So it just lays right on top of it. And when the 2 points are on top of each other, we get the tangent line. So that's how we're going to try and attack this. All right, before we begin, we need to recall how to find the equation of a line through 2 points. So given any 2 points, x1, y1, and x2, y2, we can find the following. First of all, if you're given 2 points, you can find the slope of the line between the 2 points using the old formula from college algebra, rise over run. It's the difference of your y coordinates divided by the difference of your x coordinates. In this case, y2 minus y1 divided by x2 minus x1. So we're taking the second point and we're subtracting the coordinates of the first point. Then once you have the slope of the line, then you can use this equation, which is called the point slope formula for a line. And it says that the equation of the line would be y minus y1 equals m times x minus x1. Here m is this slope, y1 is this coordinate of the first point, and x1 is the coordinate of the x-coordinate of the first point. So that we should be able to do from college algebra. And here's how we did it. You take a point like the point x1, y1, which is negative 1, 2, Then we take a second point, x2, y2, which is 5, negative 4. Now, we draw a line, and we're trying to find the equation of that line. So what we do is we find the rise. So the rise would be the difference of the y coordinate. So I'm taking the y2 and subtracting the y1. So I'm taking the negative 4 and subtracting 2. So negative 4 minus 2 is negative 6. So my rise is actually down 6. And then my run is from left to right. It's my x2 minus x1. So it's my 5 minus negative 1. 5 minus negative 1 is positive 6. So I've got my rise and I've got my run. So now let me try and put together the equation of the line. Using the formula up here, it's y minus y1 equals m times x minus x1. So I do y minus 2. That's because for y1, I'm using 2. Then equals m, which is negative 1. I got negative 1 by taking the rise and dividing by run. So I did negative 6 divided by 6. That gave me negative 1. And then I have x minus x1, but x1 in this problem is negative 1. So I'm subtracting a negative, it becomes plus. Now I distribute my negative through, so get negative x minus 1. That's a typo. I have parenthesis there, it doesn't belong there. Then add 2 to both sides, and you get this equation, y equals negative x plus 1. And you can see that this line, if you remember from the equations of lines, negative x plus 1 means that I should have a y-intercept of 1, which it is, and a slope of negative 1, which means that to get to the next point, I should go down 1 over 1, down 1 over 1. So that is the equation of that line. Okay, so let's try a different problem. All right, it says, finding the equation of the line through 2 points on a function. So instead of me just throwing 2 points out there, I want these 2 points to live on a function. Here's the function right here. Now, it says, let's find the equation of the line through negative 1, 2, and 1, negative 2. And I say, notice that these points lie on the graph of f, since negative 1, 2 is negative 1 f of negative 1. Now, what does this mean? Well, if I plug negative 1 into this function for x, you plug it in here, you get negative 1 cubed is negative 1 times 3 is negative 3. And then if you do 5 times negative 1, you get negative 5, but then we're subtracting. So it's going to become negative 3 plus 5, which is 2. So the ordered pair negative 1, 2 is really the ordered pair negative 1, f of negative 1. The function evaluated at this x coordinate. Then 1, negative 2 comes from plugging 1 into the function. If you plug 1 into the function, you get the 2, and you can check it. Just plug 1 into each of those. And I'm sorry, you should get negative 2, not 2. I said 2. I meant negative 2. So these 2 points do live on this graph. So let's go ahead. I'm going to open this up just a little bit. Okay. Let's get that first point. So there's the point negative 1, 2. And remember, that's negative 1 f of negative 1. Then my second point, excuse me, is my x2, y2. That's what I get when I plug in 1 for x and then 1 into the function gives me my y coordinate of negative 2. I'm going to try and come up with the equation of that line. So my rise is going to be, now notice the way I wrote this. It's y2 minus y1. Well, y2 for me is f of 1. So that's why I put f of 1 here. Minus y1, but y1 for me is f of negative 1. So I'm saying that the rise is f of 1 minus f of negative 1. And then, of course, those 2 points are, those 2 numbers are negative 2 and 2. So I'm taking negative 2, subtracting 2, get negative 4. So my rise is negative 4. The run is my x2, which is my 1, minus my x1, which is negative 1. So again, 1 minus negative 1 is 2. So my slope of my line will be my rise divided by run. So my slope should be negative 4 divided by 2, which is negative 2. Let's keep that in mind. Here's the equation. Here's the point slope formula of a line. I replace my m with negative 2. I replace my y1 with negative 2. That comes from right here. I'm replacing my y1 with 2, but there's the minus sign, so replace it with 2 there. I replace my x1 with negative 1 right there. And if you do the algebra on this, you get the equation of the line, which is y equals negative 2x, which means that I should, since there's nothing out here, I should have a y-intercept of 0. Then to get to another point, I should go down 2, 1, 2, and to the right 1, 1. So notice the scaling of the y and the x-axis are a little different here. This is negative 5, so negative 2 over 1 would be my slope. So that line, that equation does generate that line. Okay, now let's take a look at trying to come up with a formula, a general formula for any function, trying to find the equation of the line through 2 points on an arbitrary function. So here's the way I'm going to do this. Instead of giving you exact values to plug in, we're going to just say, let's let x1 and y1 be a f of a. So that means whatever number you plug in a, that's the x-coordinate. F of a is the y-coordinate. We don't know what that is because we don't even know what the function is. And then x2, y2 is going to be x f of x. So we're plugging in x for x, and then f of x will be our y-coordinate or our y2. So be sure you recognize that when I just chose to make my x1 a here and my x2 x, I could have picked anything. I could have called these, whatever I wanted. I could have used a and b or c and d. Then this would be f of a, f of b, or f of c and f of d. It doesn't matter. That's going to come up a little bit later. So just keep that in mind. Okay, so again, let's take a look at, now this is just imagine that we don't know what this function is, okay? It's just something. And I want to pick my first point. So my first point is this point right here. Hold up real quick. Okay, sorry about that. Can't stop my phone from ringing. Okay, so I picked my first point. Again, I don't know where this is, but I'm saying that the x-coordinate is a, so whatever this is, it's a, and then plugging that into the function, I get f of a. So there's my point, my first point. My second point, I'm plugging in x, so I'm going to say just some x value, and then f of x in this case comes down here. So I've got my two arbitrary points on some arbitrary function. Now the line I'm trying to figure out is this one. Now to show the rise, remember your rise is y2 minus y1. For us, y2 is f of x. For us, y1 is f of a. So my rise will be f of x minus f of a. I don't know what these are, so that's what I have to write. My run is going to be my x2 minus x1. x2 is x, x1 is a, so it becomes x minus a. So now I'm just going to show you the slope real quick. The slope of this secant line, right? This is a secant line because it passes through 2 points on the curve. My slope of my secant line is the rise, f of x minus f of a, that's this, divided by the run, which is x minus a. And therefore, the equation of the line, y minus y1 equals the slope of the secant line times x minus x1. So this is the point slope formula for a line. Now, my slope of my secant line is this big ugly thing in here, right? That came from this. The x minus x1 is x minus a, and that's because a is x1, right? And then my y1 is actually, where is it? Y1 is here, that's f of a, so I replace that with f of a. This is the general equation that we're going to have for the secant line through 2 points on our curve. I believe that's what I say next. Yep. So if we pick two arbitrary points on a function, a f of a, x f of x, we have these two major results. First of all, the slope of the secant line through those 2 points is this, and then the equation of the line through those 2 points is this. So this just gives you the slope, this gives you the entire line. Now let's go back and look at this geometrically again. What's happening here? We take this, and remember we're trying to get to the tangent line, right? So how are we going to get the tangent line from this secant line? I have my first point, I have my second point. I'm going to draw a line. Now I'm supposed to drag and move this point closer and closer, closer and closer, closer and closer until I get to the actual tangent line. I'm not going to zoom in again on that, right? I'm trying to get to that. Now when I get there, boom, we have something happen, and it's not good. So let's take a look at what the problem is, because there is an issue, all right? And here it is. The problem we run into from this demonstration right here is that when the second point actually becomes the first point, our formula for the slope of the secant line becomes undefined. So check this out. If my first point is a f of a, and my second point, I drag it so that it becomes also a f of a, right? Because they're right on top of each other. They should have the same exact values. Then the formula for our secant line, which was what? F of x minus f of a over x minus a, but this became f of a, and this became a right there. I become this, f of a minus f of a, which is 0, over a minus a, which is 0, and 0 over 0 is undefined. So what in the heck are we going to do? Well, that's why this is called calculus, okay? We're going to have a workaround. We're going to have a way to deal with this. We're faced with the idea of 0 over 0, which is undefined. It seems impossible for us to ever be able to get to an answer. But one of the most important concepts that we've had in this class up to this point is the whole idea of the limit. We've had limits, and we've seen limits in the past where we got 0 over 0 and we did something, and we took a limit to try and figure out where it was headed, what it was doing. It's obvious that the slope of the secant line is approaching something, right? I mean, like when I come up here and I do this again, I mean, that secant line has a slope. And as I move it over here, I mean, it is getting closer and closer to some specific slope, right? It's just that when I get to the actual point right on top of each other, boom, I can't do the algebra for that. I have division by 0. But it's going towards something, right? It's sloped this way. It's obviously not sloped this way. So there's something it's headed towards. I just need to find it. So the limit is going to allow us to be able to figure this out. Our workaround for this is going to be to take a limit. So what we will do now is we will define the slope of the tangent line, okay, the tangent line, not the secant line, to be the limit as x approaches a of this. See, because if I let x go to a, this gets close to a, and that becomes close to a, and so we will get something that looks like 0 over 0, but it's in a limit, so we should be able to get an answer. So just remember, this is just the limit of the slope of the secant line as x approaches a. So we're letting x get arbitrarily close to a. So what will happen now is when we come to this, we take our 2 points, we draw our line, we start dragging this thing over, and then right when we start getting close, right, we're going to now get to the issue where we're going to be right on top of the other point. Well, to get around that, we will apply a limit, a calculus limit, to figure out what that's headed towards, and boom, when we get there, we will actually have the tangent line. We'll have a slope. All right, so we'll be happy. All right, so now we get to the definition. The slope of the tangent line at a point, a f of a. If someone gives you a curve, y equals f of x, and some point on the curve, a f of a, we define the slope of the tangent line at that point to be the slope of the tangent line, which is just the slope, is equal to the limit as x approaches a of f of x minus a over x minus a. You might recognize this from college algebra. That part right there, we called that the difference quotient. That's why you saw it in college algebra, because we're going to use it here. Now remember, since we're taking a limit, we need to make sure that this limit exists. We saw that sometimes limits don't exist, so when that happens, you may not have an answer. But in this case, this will at least allow us to try and get a slope of a tangent line. All right, here we go. Trying to find the equation of the tangent line at a point here. So if we have the old point slope formula for a line, right, and we want to try and figure out the equation of the tangent line, then this equation will become this. Now why? Well, remember, y1 is f of a, right? That comes from this point right here. That's our y1. And then our x1, right? Our x1 is a, that's this. But the slope here is actually going to be a limit. So to figure out the slope of the line we're trying to find, the tangent line, we're going to have to apply a limit to determine what m is. So we'll take our point, take our second point, draw the line, boom, drop it in there, bam. That line right there has this equation. That's the equation of the line. So I'll do some examples in class, and then, really, this is all just to get you to understand what's happening. You'll see when we start doing examples. The algebra is going to be the challenge, but hopefully you're getting the idea of what we're doing from this. Okay, now, there is another way to look at all of this. It's a second approach, and here's the way it works. Earlier, I chose a f of a, and I chose x f of x, and those were the 2 points on the graph. And I said that we could have chosen anything, could have plugged in a and b or c and d. But now what I'm going to do is I'm going to pick my x1, y1 to be a f of a, so nothing's changed there. But my second point, x2, y2, is going to be a, which is this a, plus something, plus h, plus some value. And then, of course, the y-coordinate will be f of a plus h. That's whatever I get when I plug a plus h into the function. So let me just show you real quick what this looks like on a number line. If I pick some point a, f of a, of course, f of a lies on our function somewhere. I'm not even showing that to you. But the a is the x value. So for distance from here to here is a. A plus h, right? Here, first of all, I add some h to it, right? So here's h. I'm adding it to a. And therefore, I get a second point, which is a plus h. And then, of course, I could plug that value into the function. I would be somewhere. But I just want you to see, instead of using a here and x, I'm using a and then a plus something, a plus h, to get to my second point. Now, when we do this, let's see how things change. Okay, I have these 2 points now. And my first point here is a f of a. My second point is a plus h, f of a plus h. Still want that line, right? I'm just trying to find the equation of the line through these two. My rise is y2 minus y1. So what changes here is, instead of using the f of x that we had earlier, it's f of a plus h minus f of a. So that's my rise. My run is a little weird. It's x2 minus x1. x2 is a plus h. x1 is a. So when you do a plus h minus a, the a's cancel and you just get h. I know that's kind of hard to see there, but that's just h right there. So my run is h. My rise is this. So the slope of the secant line, okay, the secant line that goes through those 2 points, is f of a plus h minus f of a, that's my rise, over my run, which is just h. And then we get a new equation. Using this, right, from earlier, y1 is still f of a, right, that's right there. x1 is still a, but now the slope of the secant line, this part is a little bit different, right? That looks different than before. We used to have f of x minus f of a over x minus a. Now we have this. So we're just going to go through everything again. If we pick our 2 points and we define them this way, then our new secant line slope becomes this, and our new equation of our secant line through the 2 points is this. So when we try and do this again, we take our 2 points, we draw a line, and now what I'm going to do is to make this point move towards this point. What I'm going to do is I'm going to let, instead of x approaching a, I'm going to let h become 0 or get close to 0. Now, why is that happening? Well, let me take you back up here. Right here in this picture, if this was a and this was a plus h, so this is the h, it's the distance between them. If I let h get smaller, those 2 points try and come together, right? So when I want to try and move this point closer to this one, I need its x value to start moving closer to this x value, which means I need to let my h go to 0 to make those 2 points come together. All right. Oh, hold on. We're going to have a problem. Let's get there. Boom. We still have that problem. What's the problem that we run into? Well, when those 2 points become the same, right? When h goes to 0, the a plus h becomes a, and the a plus h in here becomes a, so we still have that same old 0 over 0, and that's a problem. But again, we can just apply the limit, right? This is just saying the same thing I did earlier. We're going to apply a limit to work around this. The difference is that our limit, instead of saying x approaches a, we're going to say h goes to 0. So if we take the limit as h goes to 0, what would we get here? If h goes to 0 here, we have f of a minus f of a, which is 0, over 0. So we have 0 over 0. But in a limit, we should be able to come up with some answer for this. So if that limit exists, we'll be able to find the slope of the tangent line. Okay? All right. Let's go ahead and run through this. Just to be clear, we have 2 points. We draw our line. We go ahead and draw this thing through here. Let h get closer and closer to 0. We already know that when we get there, we get the division by 0. It's undefined. But taking a limit instead, boom, we know we will get a tangent line. So the definition here, given a curve, y equals f of x, and a point on the curve, a f of a, so this is exactly the same as before. The slope of the tangent line, that's exactly the same, will be m tan, which is m, which is, this is a typo. This should say h goes to 0. The limit is h goes to 0 of f of a plus h minus f of a over h. So that's our new second version of the slope of the tangent line. And since we have a second version of the slope of the tangent line, we're going to have a second version of the equation of the tangent line. So if we try and find the equation of the tangent line at some point on our curve, we use the point slope formula. Y1 is f of a, x1 is a, but now our slope is this limit instead of the one from before. So you can use either one of those formulas to find the slopes of tangent lines or equations, the first or the second version. So when we do this, we drag that line over, bam, that tangent line has this equation. All right? So let's summarize everything here. If someone gives you a curve, the slope of the tangent line at a point is the first formula I gave you or the second one. You get to choose, all right? Provided those limits exist. The equation of the tangent line, right? If you're given a curve and you're given a point, the equation is this one or this one. Again, you get to choose. Sometimes it'll be easier to do this one than this one, or vice versa. You'll see as we work through some of these examples. All right, the derivative of a function f at a number. So the two formulas for the slope of the tangent line I already gave you. They're so widely used, okay? We are going to use these so much that we have a special name and notation for them. Those limits are called the derivative of f at the number a. So when you see this limit right here, that's the slope of the tangent line at a. We will use this notation right here. F prime of a is the way you say that. Or you say the derivative of f at a, or f prime of a. Either way. So f prime of a is equal to this limit, or since this limit and this limit give you the same thing, you could say f prime of a equals this limit. So now I do some examples, and let's see how this derivative, right? That's what we're calling this, the derivative of the function. Let's see what it represents. And we'll really get into this later, but just to wrap up this section, the f prime of a, or the derivative of f at a, as the instantaneous rate of change. The derivative of f at a not only represents the slope of the tangent line to the curve, it also represents the instantaneous rate of change of the function at that number. So what I'm saying is this, is that when you look at this, okay, this line here, the secant line right now, represents the change in the function between this point and this point. How much is it going up by? All right. Well, that's what's happening on an average, on an interval. When we drag it and we drop it right on top, what we're doing is we're saying that the slope of this tangent line is actually how fast this function is changing. The steeper it is, the faster it's changing. The flatter it is, the slower it's changing. And of course, if it's pointed in the other direction, down, then it would be changing negatively. So we'll investigate all that a little more later, but just remember that the derivative is also the instantaneous rate of change of a function. And then we can also look at it as instantaneous velocity, but we have some special conditions. If s equals f of t is a curve where s is the linear displacement of an object at time t, that is, the curve represents distance versus time, then the derivative of a is equal to v of a. We call this the instantaneous velocity of the object at time A. So, all right, what does this mean? Well, let's take a look at something here. If I take a point and notice this graph, this is time in hours. So imagine this is someone driving to school or something. This is the time that they're traveling. This is the distance they go. So at time 0, they've gone 0, right? They're at 0, 0. Now I'm going to pick a second point, and let me move that second point all the way to the end. So what happened is they started out at 0 hours, they have gone 0 miles. At 1 hour, they had gone 10 miles. So what we can do is we can draw the secant line, okay? There's the secant line. The secant line connecting these 2 points, if we take the rise over run, rise is here 10, and run is 1, 10 divided by 1 is 10. So the slope of this purple line is 10. And that 10 represents your average velocity, your average speed. You went 10 miles, right? 10 miles in 1 hour. So you went 10 miles an hour. But the actual curve that shows your how fast, the curve actually shows where you were at every point in time. It looks like you started off slow, and then towards the end, you traveled a greater distance in less time. So when you go 10 miles, and when you say you go 10 miles an hour to get to work, you're not driving 10 miles an hour the whole time. That's what the secant line's saying. It's like you're going 10 miles an hour all the time. That's not the case. So what we want to do is we want to try and figure out what's happening at certain points. So let me try this. Let's go and look at what's happening in the first half hour. So in the first half hour, I went from here, half an hour, to here, right, 0.5. How far did I go? Well, you can't really tell, but the distance up here divided by this time is my average speed, and that would be 1.25. So my average speed for the first half hour is 1.25. Now, in the second half hour, this to 0.5. So I'm moving my first point to 0.5, my second point to the end. Now, in the last half hour, I was traveling an average speed of 18.75 miles per hour. So in the first half hour, I wasn't going that fast on average. In the second half hour, I had to go a lot faster on average. But this class is not about what's happening on an interval, on an average speed. We want to know what's happening exactly at a point. So like exactly at 0.5, how fast was I going then, right then? So what I would have to do is I would have to try and drag that other point towards it, right? And I would try and get as close as I can get. I would try and get as close as I can get, and then finally drag it right on top, and that would give me the slope of that line at that instant, and that would give me the speed at that instant. So I'm going to start stepping down here closer and closer. Oops, geez, I went too fast. And then getting closer and closer. So look at what my speed is, 5.468. And then even closer, it's 5.1, 5.091. It's getting really, really close to, well, you probably guessed it by now, my instantaneous velocity or speed at that point in time, exactly at half an hour, was, boom, the slope of the tangent line, which is 5. So at exactly half an hour, I'm traveling, at exactly that moment, I was traveling at 5 miles per hour. So if you look down at the speedometer, that's what you would see, 5. Now this is going to change if I change my point. If I move this guy over, let's say, drag him over here, and then try and find the instantaneous rate of change at that point, dragging the other one, I need the slope of the tangent line here. That's going to be a little different. Look at that. My speed is 17.49. So you can see that the steeper this line is, the faster I'm going. So back over here, my tangent lines are flattened out, so I'm going pretty slow, but over here, they get steeper and steeper, which means I'm going faster and faster. So that, again, is how we can tie the derivatives and the slope of the tangent line to the speed of an object at some point in time, the instantaneous speed. All right, that's it for now. We'll start section 2 in just a moment.